What is common between water in a canal, guns having barrels, optical fibers, and a stethoscope? And how is any of this related to waveguides? Well, they're all based on the principles of constrained motion. Like a gun restricts hot gas expansion to maximize energy transfer to its bullets. The oldest and most original meaning of waveguides is a hollow conductive metal pipe which is used to carry high frequency radio waves, particularly microwave.
Some interesting things you should know about waveguides. A waveguide confines the wave such that under ideal conditions the wave loses no power while propagating. Due to total reflection at the walls, waves are confined to the interior of a waveguide. Waveguides were used even before we had given it this name. We can construct waveguides either from conductive materials or from dielectrics, depending on what frequency we want to transmit. Dimensions of a waveguide depends on what frequency we are using. It will be large for a smaller frequency and a smaller for higher frequencies. Now have a look on some of its applications. Optical fibers transmit light and signals for long distances with low attenuation and a wide usable range of wavelengths. In a microwave oven, a waveguide transfers power from the magnetron where waves are formed to the cooking chamber. In a radar, a waveguide transfers radio frequency energy to and from the antenna where the impedance needs to be matched for efficient power transmission.
In this slide, we see how a wave interacts with the boundary of a waveguide. The material too in the picture is a PEC. PEC, or a perfect electronic conductor, is a material that has permittivity equal to minus infinity for a particular range of frequencies. This kind of material is responsible for perfect reflection. No transmission happens through this medium. That is why we can see that the wave gets reflected back on colliding with the second medium. A propagation mode in a waveguide is one solution of the wave equations, or in other words, the form of the wave which will exist. Due to the constraints of the boundary conditions, there are only limited frequencies and forms for the wave function which can propagate in the waveguide. The lowest frequency in which a certain mode can propagate is the cutoff frequency of that mode. The mode with the lowest cutoff frequency is the fundamental mode of the waveguide, and its cutoff frequency is the waveguide cutoff frequency. A general wave equation can be written as: let us try and find the equation of waves inside a parallel plate waveguide. Without the loss of generality, we can assign the direction of wave propagation to be z. Hence, kx equal to 0. Since there is total internal reflection in y direction due to the presence of a PEC, there will be a standing wave in y direction. The wave traveling towards positive y will have ky greater than 0, and the wave traveling towards negative y axis will have ky less than 0. These two waves in combination will give out a sine or a cosine function. Applying boundary conditions, we can get d1 minus d2 equal to sigma f and d2 equal to 0. Here d is the electric displacement. Also, we can get E1 parallel is equals to E2 parallel equal to 0. Using these, we can get the equations for Ex and Ey. Here, z is the direction of propagation and kz is the propagation constant. Sine into kya is equals to 0, which implies ky equal to m pi by a, where m belongs to integers. We know that k square equals to kx square plus ky square plus kz square. Here we assume that kx is equals to 0. So k would be equal to k square would be equal to ky square plus kz square, which in turn would be equal to omega square upon c square. From that we can conclude that kz equals to under root of omega square by c square minus m pi by a whole square. This is true for a parallel plate waveguide or a microstrip. From this, we see that the phase velocity, the expression for which is omega by kz, is greater than the speed of light. This might look and sound weird, but remember, the phase velocity of a wave corresponds to the propagation speed of a theoretical single frequency component of the wave at that frequency. Such a wave component must be infinite in extent and of constant amplitude, and so cannot convey any information. Thus, a phase velocity above c does not imply the propagation of signals with a velocity above c. Also, the group velocity here is del omega by del kz, which is less than c. Thank you.